Hi guys, there's a question about a problem from section 1.7. Section 1.7, one of the homework problem number 17. A student had a question about it. This is actually a very special type of linear inequality. Kind of what I usually refer to as two extreme cases or special cases because of what happens pretty much at the toward the end of the solving the inequality. Okay, so anyway, it's still linear, but it is kind of special. So let me go ahead and work it for you, and then actually once I finish this, I'll tell you the other extreme case, because there are two extreme cases, but they both kind of happen the same way. So I'll talk about that after I finish this one. So we have the following linear inequality. So again, as always, to solve any linear inequality, you want x on one side. So before we can even isolate the x, we have to remove the parentheses. So by distributive property, as we distribute that, that becomes 3x. 3 times 5 is 15. And of course, everything else still there. And then of course, 15 and 1 add up to be 16. So now, obviously, we want the x on one side. So we have to remove one of the 3 x's from the either side. So I'm going to go ahead and subtract 3x from both sides. And this is where kind of the special thing happens, right? I'm sure all the problem that you did, most of them, this didn't happen for these types of inequality, but this is what's special about it. So if you notice, those cancel each other. So you're left with 16. But also as a coincidence, these two cancel each other. So anytime you have the same exact x term on both sides, that's usually when these special cases happen, okay? Now, here's the thing. You still have an inequality, so it's nothing wrong. You didn't do anything wrong if you notice the x's went away, because this is what makes it special. But the question is, what's the conclusion? So once all the x's go away and you have your final inequality. Now, if this inequality is a true inequality, then you say all real numbers are your solution. So this is one extreme. Of course, in this case, it is true because 16 is greater than or equal to 5. Therefore, this is true for the solution is all real numbers. Of course, as you know, the way we represent all real numbers in interval notation, it will be negative infinity to infinity, which is all real numbers, okay? So I'm just going to make so this is done. I'm just going to make a quick comment. If, let's say, if you would have started with a less than or equal to here instead of greater than or equal to, which I'm sure you may have a homework like that, so everything will be the same, except down here, it will become 16 less than or equal to. So in that case, that will be false, and then you say no solution. So that's the other extreme, okay? So anytime all your x's basically go bye-bye, and you have no x left, so you just look at the final inequality. If that's a true inequality, if that's a true statement, you say all real numbers are solutions. And of course, you write all real numbers in interval notation as negative infinity, comma infinity. If this was at the end untrue statement or untrue inequality, then you say no solutions, okay? So these are kind of what we call special cases.